In our last video, we covered the first of two basic rules in probability, the addition or rule. In this video, we'll discuss the second rule, the multiplication or and rule. The multiplication or and rule says that if two events are independent, the probability of both occurring is the product of their individual probabilities. Now, what do I mean by independent? For two events to be independent, it means that the occurrence of one event doesn't change the probability of the other event. Probably the easiest example is a pair of dice. If I'm rolling two dice, whatever number I roll on the first die has no effect on whatever number shows up on the second die. If I roll a 1 on the first die, it has no impact on the probability of any of the numbers showing up on the second die. And if I roll a 6 on the second die, it has no impact on the probability of whatever number shows up on the first die. Now, when two events are independent, again, the probability of both occurring is simply the product of the probability of each of the individual events. Mathematically, we can write that as the probability of A and B equals the probability of A times the probability of B. Let's look at an example using a deck of cards. What's the probability of selecting one card that is red and a face card, a king, queen, or jack? To answer that, we need to know the probability of each of those events. So the probability that a card is red is just the proportion of all of the deck that's red, or 26 over 52, right? There's 52 total cards in the deck. Half the deck is red, all of these highlighted cards. That's 26 over 52. Then we need to know the probability of the card being a face card. Again, a king, queen, or jack. Well, that's 12 over 52, right? There are 3 face cards and they appear in all 4 of the suits. And notice that being a face card is independent of the color of the card, right? 6 of the 26 red cards are face cards, and 6 of the 26 black cards are face cards. The probability of being a face card is the same. It doesn't change based on the color of the card. So the probability of selecting a card that is red and a face card is the overlap between these two groups. In set theory, we talk about this as the intersection of these two sets, a set of red cards and this set of face cards. But visually, it's just the overlap. We're interested in the probability of this intersection, this overlap, which is, right, it's these cards right here. They're the cards that are red and face cards. So using the multiplication rule, the probability of a card being red and a face card is just the probability of it being red, 26 over 52, times the probability of it being a face card, 12 over 52. This solves to 6 over 52 if we manipulate the numbers to keep that 52 in the denominator, which also can be reduced to 3 over 26, right? Or if you write it out as a decimal, 0.1154. The probability of being a red and a face card is 0.1154, right? Now, notice how, because we're looking at that overlap, the intersection between red cards and face cards, the multiplication rule leads to smaller probabilities. the probability of this and that can't be larger than whatever was the smaller of those two probabilities, right? It's not just this anymore. It's this and it has to be that. The probability gets smaller. If you end up with a result that's larger than the smaller of those two probabilities, you know you've made an error somewhere. All right? Now, let's dig into this a little more with a different example, going back to dice. Let's say that I'm rolling 5 dice, and I'm interested in the probability that all 5 of them land on a 1. How would I estimate that? Well, why don't you pause the video for a moment and see if you can figure that out. Well, I need to translate all 5 die land on a 1 into something that's a little more statistic speak. The key is to recognize that that's exactly the same thing as asking for the probability that I roll a 1 and a 1 and a 1 and a 1 and a 1, right? And each of those are independent of the others. See that? Whatever I roll on one die doesn't influence the probability of whatever I roll on another die. So we can use the multiplication rule and estimate the probability as the probability of a 1 times 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 the probability of a 1. Whew. Well, the probability of rolling a 1 on a 6-sided die is just 1/6. So this works out to 1/6 times 1/6 times 1/6 times 1/6 times 1/6. That solves to 1/6 to the 5th power, or if I calculate that denominator of 6 times 6 times 6 times 6 times 6, I get 1/7,776. So I can write this out as the probability of rolling 5 ones is equal to 1/7,776, or 0.000129, right? Good. Okay, now let's take this problem one step further. There's a dice game called Yahtzee where you roll 5 dice and get points based on different combinations of values that show up in those rolls. A Yahtzee is where all 5 dice have the same value, and that's worth the most points. Now in the game, you can do this over 3 tries where you can keep some dice and re-roll others. But we'll keep it simple and ask, what's the probability of getting a Yahtzee on a single roll of all 5 dice? In other words, what's the probability that all 5 dice have the same value on one roll? Now, it can be any value. It can be a 1 or 2 or 3 or 4 or 5 or 6. But all 5 dice have to have the same value. Okay, why don't you pause the video again for a moment and see if you can figure this one out, okay? To answer this, we'll break the problem into 2 pieces. First, we'll use the multiplication rule, just like we just did. In this case, what's the probability that all 5 dice would be a 1? Well, right, we just saw that. That was 1/7,776, right? And based on that, if you think about it, it's probably not too hard to see that the probability that all 5 dice are a 2 is also 1/7,776, right? As would be the probability that they're all 3s or all 4s or all 5s or all 6s. Each of those has the same probability of 1/7,776. Now, the second part of solving this problem involves using the addition rule. Notice I can get a Yahtzee by rolling 5 ones, or 5 twos, or 5 threes, or 5 fours, or 5 fives, or 5 sixes, right? Notice all those ors. It can be this, or this, or this, or this, or this, or that, right? And each of those are mutually exclusive. See that? If you rolled 5 ones, you could not have rolled 5 twos. If you roll 5 threes, you couldn't have rolled 5 sixes. So that tells us we can add up those individual probabilities to get the probability of rolling 5 ones, or 5 twos, or 5 threes, or 5 fours, or 5 fives, or 5 sixes. Well, that is just 1 over 7,776 plus 1 over 7,776 plus 1 over 7,776 plus 1 over 7,776. I was never going to make that. Plus 1 over 7,776 plus 1 over 7,776, which solves to 6 over 7,776. So the probability of a Yahtzee on one roll is just 6 over 7,776, which reduces to 1 over 1,296, or 0.000772. All right? Now, before wrapping up, let's touch on one final point. So far, with the multiplication rule, we've only considered situations where things are independent. You know, rolling several dice, things like that. But what about if two events are not independent? Or more formally, what if they lack independence? Now, what do I mean by that? What do I mean by lack independence? Well, two events are not independent. They lack independence when the probability of one event varies based on the occurrence of the other event. In other words, the probability of one event is different depending on what happened in the other event, on the value for that other event. To see that, let's look at the Titanic, right? The probability of a passenger surviving the sinking of the Titanic was 0.38. 38% of the passengers survived. And the probability of a passenger being in first class was 0.25. 25% of the passengers were in first class. If we just assume that the probability of surviving and being in first class are independent, then the probability of someone being a survivor and being in first class is just equal to 0.38 times 0.25, or 0.095. But that's wrong. The actual probability that a passenger was a survivor and in first class was 0.153. What happened? I mean, why? What happened here? Well, it's because they're not independent. I mean, we all saw the movie, right? Although some of us regretted it halfway through. I swear I was rooting for the iceberg by the end of the movie. But I digress. When it came time to get on the lifeboats, the decision was not made independent of class. More first-class passengers got a seat. When data lack independence, things get a little more complicated. But that's beyond the scope of this introductory series, all right? Now, we'll revisit the Titanic and this question of independence later on when we learn the chi-square test. All right. But with that, let's wrap up this video on the multiplication or AND rule, all right? Take care. Bye for now.